Hello, my name is Moran, and this summer I researched analog circuits for embedded model predictive control. I worked with Dr. Adebega in the College of New Jersey's Lab for Embedded Control Optimization. So as an introduction, embedded analog circuits have been looked into due to their ability to efficiently and accurately perform computations relating to control. However, there is yet to be a comprehensive study of control implementations of these circuits. Some of these possible controllers include proportional integral, low-gain quadratic programming, and model predictive controllers. This past summer, I've worked on implementing these controllers and testing them on the quadruple tank control testbed. Although many of the controllers were implemented, the focus of this research was on model predictive control. This method of control aims to minimize a quadratic programming problem to find an ideal control output. MPC also incorporates constraints into the minimization. These constraints come from real-life data and limitations and help push the plans to its limits, resulting in optimized control. Below is the minimization problem used, with minimizing a variable u with certain constraints. So in order to implement the minimization problem, we have to convert it to a differential equation. And it's implemented as an analog circuit this way using gradient dynamics in the following equation, where u dot equals negative u plus a saturation of u minus hu minus q. In order to effectively implement this differential equation as an analog circuit, it is necessary to break it down into its arithmetic components. This includes summing, integration, and saturation. All of these operations can be implemented using a combination of op-amps, resistors, capacitors, and diodes, all of which are common analog devices. Examples of these circuits are shown to the right. However, in order to streamline all of our circuits, a field programmable analog array was used. An FPAA also allows an analog circuit to be programmed and downloaded onto a chip for fast, rapid, and accurate prototyping. For my experimental setup and results, as mentioned previously, all the testing done on these circuits was completed using the quadruple tank system. This system is comprised of the coupling of two sets of vertically positioned tanks. The control objective was to set the water levels in the bottom tanks to a desired level, seeing the results as the reference. The control architecture is shown below, with feedback from sensors into the controller and the controller determining the flow of rate being defining features. In this experiment, all four controllers were stepped to the reference point at time equals 0 and run for 200 seconds. As seen in the results section in the bottom middle, all four controllers converge to the solution, showing the working of complex analog control. The variable u on the bottom shows the control output, which is the voltage to the pump and the flow rate, and the variable y, the tank height. As you can see, both converges to 10 and 14 centimeters, exactly where the reference points them to. So for future work would be to implement this model on a different physical device. One possible candidate would be the Quantum 2 degree of freedom helicopter. This system models air or underwater vehicles and will provide a reliable model to test all four of our controllers on different hardware. Thank you.